This is a walkthrough video of a tank mixing simulation in Ansys. I'm going to start by creating a new system in Fluent, and I will open Design Modeler to create the geometry. I will change my units to inch and begin by drawing the overall tank. On the XY plane, I'm going to create a new sketch and draw a circle centered at the origin with a radius of 24 inches. I'm going to then extrude this asymmetrically 30 inches in the positive z direction and 5 inches in the negative z direction. If we go ahead and generate it, we can now see our overall tank. The next step is going to be adding the propeller. To do this, I'm going to start by hiding the tank. And because we need the propeller at an angle, I'm going to start by creating a new plane, which is rotated about the x-axis by 45 degrees. On this plane, I will create a sketch and draw the shape of the propeller blade. The propeller has a radius of 7 inches, and we will do a width of 4 inches. To center it on this axis, I will create this dimension with 2 inches. And I will go ahead and extrude this symmetrically, 3/8 of an inch in either direction. And instead of adding material, I'm going to slice material. When we generate that, we will be left with our fin along with the tank with the fin subtracted from it. This blade I'm going to pattern. So I'm going to start by creating another sketch on this XZ plane with just a line that we can use for our pattern. I will give this a dimension. .30 inches, so it's the top of our tank. And then create a pattern of our blade. We want a circular pattern about this axis that we just drew, and we want 3 copies to make 4 fins in total. Next, on the XY plane, we will draw the shaft. So I'm going to draw another circle on this plane, centered at the origin. And we'll give this a radius of 2 inches. And extrude it like the vat, asymmetrically, 30 inches in one direction, and we will do 2 inches in one direction to leave a 3-inch gap between the bottom of the shaft and the vat floor. Instead of adding material, again, we want to slice, but we only want to slice through the tank. So I will select the tank and generate this. We now have our shaft of the propeller. The last thing we will do for the propeller is subtract all of these bodies from the tank. So I made a Boolean. I will do subtract. The target body is the tank, and the tool bodies are our propeller blades and the shaft. If we generate this, we're left with one body, which is the tank with the propeller cut out of it. Next, I will add the baffles. I'm going to create a new plane on the bottom face of the tank and create a sketch on this plane. I have to generate it first. Create a sketch on this plane with the cross-section of our baffle, which is a rectangle. The baffle has a width of 1/4 of an inch. To center it on this, I will add another dimension of 1/8 of an inch. It has a length of 4 inches. And lastly, I will make the outside edge of it tangent with the edge of the tank. I'm going to go ahead and extrude this. We are once again going to slice material, and for the extent, we're going to go through all. We now have one baffle cut out of our tank. We are going to want to pattern this, so we will again make this axis visible and create another circular pattern of our baffle about the same axis, evenly spaced with 3 copies for 4 baffles. Like the propeller, we are now going to subtract our baffles from the main tank and generate that. And once again, we have one solid body with our baffles cut out of it and the propeller cut out as well. The last step is going to be splitting the body of the tank into 2 regions. This is necessary so that we can move the propeller relative to the baffles and the outside of the tank. I'm going to make another sketch on the XZ plane. And the cross-section of this revolve is a rectangle. So I will draw another rectangle, give it what is effectively a radius of 10 inches. The bottom of this will be 3.5 inches from the center of the propeller. And finally, we want the top of this coincident with the top of the tank. We can now revolve about the center axis and slice so that we have 2 regions, one containing the baffles and one containing the propeller. That's all for the geometry, so we can save our project, close this, excuse my computer noises, and we'll open the meshing. We can start by generating a mesh to see what the initial mesh looks like. And the first thing we're going to do is increase the resolution on the baffle. So we'll go into mesh, add a sizing, and select all of the faces of the baffle. I'll apply this geometry, and we will set an element size of 0.05 meters, regenerate the mesh, and we'll see that there is now slightly higher resolution on the baffle itself. The next step will be increasing the resolution on the interface between the 2 regions of the tank. This is helpful to make the interpolation a little better between these regions. I'm going to start by hiding the inner region so that we can see the interface. We will create another sizing, first on this face at 0.05 meters, and second on the bottom face of 0.03 meters. We can generate this and take a look and see that we have a much finer resolution here. We're going to do the same thing on the inside region because we want the meshes to be roughly similar between the two interfaces. So I will go into mesh, do a sizing on this face of 0.05 meters, and another sizing on the bottom face, like the outer region, 0.03 meters. We will generate this and see that it looks similar to our outer region. The final step is going to be increasing the resolution on the propeller itself. I'm going to start by hiding this face so we can see the propeller blades. And we'll do one more sizing of all of the faces of the propeller as well as the shaft. So this will take a minute, but I have to select all of these faces. With those all selected, we will apply it and give this an element size of 5 millimeters. Generate the mesh one more time. And we can take another look. We see that inside the shaft has a much higher resolution. And to get a better view of this, we can create a section plane through the center and take a look, an up-close look at our propeller blades. So there's a much higher resolution now on the propeller blades, which should give the simulation higher accuracy. We can also show this body to get a better sense of the overall look of the mesh, and this will be sufficient for moving on to the next step. So we'll save the project and close meshing.
All right. Hello. I'm taking over. This is Adrian. I'm going to be walking you guys through the setup and solution for our mixing vat agitator. So we've already gone ahead and gone through the geometry and the mesh setup. These are checked off here and C. I have A and B as two different models of the same system that are already walked through. But we're going to start here at the setup. So I'm going to go ahead and double click on setup. I'm going to have this little pop-up here. We're going to go ahead and keep double precision selected. And I set my solvers to 4, so what my machine can handle. Set it how you like based on your processing power of your computer. So we're going to click start. And we're going to let Fluent load up. Go ahead and pull this over here. This might take a second as it copies the geometry and the mesh into the application. Okay, so we're back with Fluent loaded up. As you can see here, I have this pop-up warning me about matching zone names between the different meshes. And so it's throwing this error as the interface between our mesh that we've separated here between our inner cylinder and outer cylinder, as well as the two bottom interfaces on this internal zone. There's a mismatched ID. So to start off, we are going to, follow the instructions here in the pop-up. Go file, recorded mesh operations. Pull this window up, we'll go to match zone names. And then I've already gone ahead and matched them here. But I will go ahead and remove them and just go ahead and match them together. And that way we can identify. Uh, so I've gone ahead and matched up our mesh interfaces as described through mesh operations and matching zone names. Um, and so you're gonna pop this window up and you're gonna match their wall zones to the mesh zones we have in our parts. So I'm gonna go ahead and do this real quick. So then we're gonna go ahead and reload the setup, um, and then let Ansys do its thing. Okay, so sorry, the confusion. I've gone ahead and reloaded our setup again so that our model is imported alongside our mesh interface here. I will get into those in a second. Um, but Ansys has imported our geometry as well as our mesh, which is not shown here, but you can see our base geometry, the shaft, the impellers, the full fat, and the baffles, alongside our two separated mesh zones, the inner in yellow and the outer in gray. Um, so in general, I'm going to start here with a pressure-based transient solver. Um, Due to the nature of the mixing vat, a steady state assumption isn't the most accurate and it's hard to model the moment and torque that the impeller sees accurately. So as a result, we will be doing a transient solver. Um, so with that done, so oop, with that done, I'm going to go to models. We are going to leave it as a laminar model, um, likely already preset, just as is. Materials, we're going to go to fluids and select our material as water. Open it up, we can verify our density and viscosity, and we'll leave these values preset as is. They're all good. If water is not a preset liquid or fluid in the database, you can go Fluent database, and we can scroll all the way down to water, water liquid, and then we can copy all these into um, our material. And then, so I would normally hit OK, but I already have it there, so I do not need it further. So, yep, that's that. Close. Our solid we can leave as is. So that our initial setup, we're going to go to cell zone conditions. This is where we define the how the fluid is moving within our domain. And since our setup is there's two ways to go about this. We can rotate the fluid around the whole domain while keeping the impeller fixed, or we can keep a stationary fluid and rotate our impeller as we see in the actual function of the vat. So I'm going to go in order to so I'm going to go ahead and after I have my model selected as viscous laminar, we're going to go to materials. We're going to select our fluid as water liquid. If it's not already here, we can go to new, and if it's already preset, we can just click on it. Otherwise, we can enter the Fluent database and select water liquid from the list and then copy it to our fluids and create a new material. We will leave solids as is. Um, Next, we will go to cell zone conditions. This is important because it defines how the fluid is moving in our domain and what is moving. So I'm going to go ahead and click on inner region. this is the part we care about, everything relative to the impeller. Um, and so we're going to select mesh motion. What this does is this will rotate the entire mesh within the domain of liquid. So our water is stationary and the impeller will be rotating at a prescribed speed. So in this case, normally you pop up, this is your window, click on mesh motion. I'm going to go down to rotational velocity and we're going to set it. In this case, this is 60 RPMs, which is equivalent to 2 pi radians per second, and we're going to prescribe it in the negative direction. And then rotating about our z-axis, all good, and hit apply, close. Um, and then our outer region, we will prescribe to no motion, as good as is. So, go ahead and close that. I'm going to make sure our material is water for both of these, and not the default air. Next is all of our boundary conditions. And so we have our interface, wall, and internal regions. We care mostly about the walls. So everything here should be no slip except for the surface of the vat, which will just be a free slip boundary. So if we go to bottom wall, and then I'll speed through all of these. So stationary, no slip, apply, close. And shaft. Since we are prescribing a mesh motion um, within the inner zone in the inner region, we will leave the fins and the shaft of the impeller as a stationary low slip boundary condition. So this is okay. Let's go through all these. And set our shear stress at the surface to 0. Let's make it a free slip boundary. And that goes for the inner and outer regions of the surface, as defined by our 2 separate zones. So no shear here as well. And then finally the walls will have, once again, should have a no slip condition. And so next we're going to have our mesh interfaces. Um, so if I click on interface 1 or create new, I can align the corresponding interface zones I care about to the correct interface. So in this case, we're going to do the bottom of the 2 different cell zones. So we have bottom of the inner, bottom of the outer. Select those 2 together. So together right now, apply, close. But in this case, I would create new, but I already have it created. So I'm gonna go to interface 2 and select the inner and outer of the cylinder walls of our 2 zones. Apply, close. Hmm. So to create a new mesh interface, what I do is I click new. Over here, select the 2 interface zones that I want to combine. In this case, it'll be the bottom of the cylinder, for the inner and outer region, and then select interface 1, and then we'll set. So next, I'm going to go over to my report definitions, and we need we need to create a report definition for our torque output or torque on the blades. So I'm gonna go to report, right click, new, force report, moment, over here, we define this as torque and select moment. I'm going to do fins and shafts, and then about the z-axis, all good, moment center 0, and then hit click OK. So now you can see we have a torque report definition down here, which will plot our torque values on the fins throughout time. Then we want to make sure there's a report plot created. That way we can visualize the output as Ansys is trying to solve our sim. And we want to make sure that we have a report plot created for the torque. That way Ansys will plot our torque throughout time as it's trying to solve the system. So that's all good. Next, we are going to do initialization, and we're going to do hybrid initialize. Once done, we can go down here to results. We are going to plot a contour plot. So I'm going to hit new contour. We'll call this pressure. And since the impeller is rotating, there's no static pressure, so we're going to do total pressure. And then we're going to deselect all our surfaces. So that we only have the impeller. So, and the banded or smooth, up to you. Doesn't really matter. It's more visualization. So we will save display. And you can get a general view of what it might look like before simulation. So great. With that done, we can go ahead and initialize our system, get a calculation. We're going to run this at a time step of 0.05 seconds for 200 time steps at a maximum of 100 iterations per time step. So after creating our pressure contour, I'm going to go ahead and backtrack to our monitors, and I'm going to go ahead and edit our residual monitor. And I'm going to leave x velocity y, x, y, and z velocity as 1 times 10 to the negative fourth, and continuity as 1 times 10 to the negative 3. So that way our simulation does not take forever. So yeah. So with that in mind, we're going to go to run calculation. Going to do a time step of 0.05 seconds at 200 time steps with a maximum of 100 iterations per time step. We're going to report every single time step. And we can leave it as fixed. And then I'm going to go ahead and calculate. So Ansys might take a while to run this as it is transient in 3D. If you're using more processors in your setup, it might take quicker. However, with our continuity converging only at 1 times 10 to the negative third, it should hopefully speed up the process. So I will let this run for a bit. As you can see already, it's converging quite nicely. So there's our first convergence of continuity, 90, -4 at 45 iterations, more or less. So we'll let this run for a bit and come back once it's fully done. Okay, so with our report definition for the torque on the impeller created, the next thing we want to do is to make sure that we can export this report file. So I'm going to go down to report files, click edit. I already have this here, so I did it earlier, but I'm going to create new, and we're going to select torque, add this over here with flow time, and then rename it to what we want. So report file torque, that'll be okay. And then we're going to rename our file name to be a .txt file. That way it will export, and then we can then import it into MATLAB via a text file. And then we'll click OK and close.
So now that your simulation is finished, you can take a look at some of the results and different graphics that Ansys can produce. Starting out, here's a plot of the moment that the shaft and blades feel throughout the simulation. This is moment on the y-axis and time on the x-axis. For this simulation, you can discard most of the beginning, as this is due to the spin-up properties of how we specifically set our simulation up with that segmented mesh and prescribed velocity. But as it kind of converges, you can see a more consistent moment throughout time. This path line graph shows you the path lines of the fluid. This is colored by particle ID just to make it easy to see. This is very good at showing us how the fluid is moving. Here you can see those tip vortices that are formed by the blades passing through the water, as well as some other circulation around the blades. Here is a contour velocity magnitude, which shows about what we expect, which is a very high velocity at the tip of the blade and around that, and then a much lower velocity throughout the rest of the vat. Moving on to some of the other results, you can see this is a simulation run on the 4-inch width blade with a 60 RPM motor. You can see here's on the top this pathline plot, which shows us those similar tip vortices. With this pathline plot, you can actually see how, as the fluid is pushed into the ground, it spreads out along the vat and up as it hits the walls, which is what causes a lot of that rotation. You can see this also reflected in this velocity contour here, where you see that similar shape of faster velocity. This bottom plot is a vorticity plot, and we can see that there's a high vorticity around the tips and edges of the blades, which is what we would expect. Looking at the moment versus time plot, here is the set of equations we use to calculate the expected moment in Newton meters given that load cell data. And for this one, the 4-inch by 60 RPM simulation, we have a very, very close result between the expected 2.17 Newton meters and the simulated 2.12 Newton meters. For the 2-inch blades, you can see very similar things. Obviously, the geometry is a little smaller, so your tip vortices are a little smaller. But you can see very, very similar trends throughout the flow, including that splashing outwards of the fluid underneath the blades. And then again, for this moment versus time plot, it's very close with 1.3 Newton meters expected and 1.21 Newton meters simulated. The 8-inch blades, again, more of the same. They're moving much more fluid, so you can see that reflected in this pathline plot where there's a lot shown going up the walls, as well as a lot of vortices around the blades as they're moving so much fluid around. Here our results are a little less accurate with a expected torque of 3.22 Newton meters and a simulated torque of 3.87 Newton meters. This is due mostly to as these blades become much closer together due to their size, the mesh kind of falls apart as flow will pass over one blade and separate and hit the next, and that laminar assumption starts to crack in some places. Here we show a 4-inch width blade between two different RPMs, so that's that 60 RPM and that 90 RPM that you may be running it at. We see very similar trends here. Of course, in the 90 RPM, you see higher velocities as it's spinning faster. and you're seeing greater vortices. So in the vorticity plot on the bottom, you're seeing very similar trends, but amplified as it's spinning much faster. Comparing the torque readings from these, we see, again, very similar results between the expected and the simulated values. Of course, it's higher on the higher RPM simulation because, again, it's moving much faster. Comparing this for all widths, we can see very similar results for the 2 and 4 inches at higher RPMs, though with the 8-inch blades, there's a pretty big discrepancy between our expected RPM and our simulated, or our expected torque and our simulated torque. And that's mostly due to because of the greater width and higher speed, your Reynolds number is really hitting that transition area into the fully turbulent range of values, so that laminar assumption is really starting to break down, which is reflected in a discrepancy in simulation results.